Hello and welcome to today's webinar entitled Advanced Scratch Testing for Evaluation of Coatings. My name is Sarah Tishner and I will be hosting the webinar today. A couple of housekeeping notes for you all. All attendees are on mute. We welcome questions. Your questions can be input into the available text box in the webinar GUI, and we will answer those questions at the end of the webinar or as time permits. For those questions that we do not get to during this session, we will respond by email or phone if possible, but be certain to address any questions you have. We also, at the end of the webinar, have an exit survey. This is a short 5-question survey, and we really do appreciate you taking the time to complete the survey to help us host more interesting webinars for you in the future. And finally, the presentation and recording of this webinar will be available online following the event. You will receive the link to the online recording and PowerPoint slides following the webinar, and also it will be posted in the chat window here shortly. So not to fear or worry, you will be able to get access to the webinar materials. And with that, I would like to introduce our presenter for today. Dr. Suresh Kuriri has a PhD in metallurgical and materials engineering from IIT in Kharagpur. He has spent several years at the University of Central Florida as a postdoc researcher and is one of Bruker's senior research scientists with 6 patents to his name. He's conducted extensive research and development in nano, micro, macro, tribology, nanomaterials, wear, tribocorrosion, chemical mechanical planarization, and electrochemistry. Dr. Kuriri has been working for Bruker, formerly CETR, for the last 8 years. He's managing research and development and applications in tribology and mechanical testing. And with that, I'd like to hand it over to Dr. Kuriri.
Thank you, Sarah. Good morning, everybody, and welcome to the Bruker webinar on advanced scratch testing for evaluation of coatings. On this webinar, I will try to cover the following topics: scratch test fundamentals, scratch failure regimes and their characteristics, existing scratch models, analytical model mostly, some are semi-empirical, CETR-UMT scratch tester, advanced scratch testing with CETR-UMT, that is Universal Materials Tester, and some scratch test results obtained using CETR-UMT. At the end, we'll have some time for questions and answers. Why we need scratch test? You know, scratch test is designed mostly for coatings, evaluation of coatings. And coatings are used for optical, microelectronic packaging, biomedical, and decorative applications. These coatings actually improve several properties, such as tribological properties, basically to lower friction, mechanical properties to increase wear and abrasion resistance of the coating, to enhance the durability of any engineering components. Coatings are also used for chemical property enhancements of any components, especially surface. When some component is exposed to some aggressive environment, such as high temperature, oxidizing environments, say for instance a turbine blade, then we put a coating to have a barrier to this aggressive environment, and this aggressive environment cannot react with the actual substrate or component, thereby enhancing the life of this component. Coatings are also used for optical, magnetic, and electrical properties of any substrate to improve these properties. Now, a coating will not work if it doesn't adhere well to the substrate. It loses its functional behavior. Hence, scratch test is very important to find out these adhesion properties of a coating. Scratch test is widely used. It is relatively fast process for evaluation of coating and an effective method to obtain critical loads that are related to adhesion properties of coating. Although scratch test is used for scratch adhesion properties of any coating, it is also used for measurement of hardness of any coating as well as a bulk material. Although this seminar is mostly based on scratch adhesion test, but I just wanted to introduce the scratch hardness test at the very beginning, just to mention it that there is a scratch test which can give you scratch hardness of coating or materials. And I will not cover this particular part in details. Those who are interested, they can refer to ASTM standard G171. In this test, scratch hardness test, what we do is basically you take a sample and a reference sample. Sample of coating or bulk materials, you use a stylus with certain load and scratch with it with a constant load. Make a scratch. Measure the scratch width on the specimen. You repeat this test on a reference specimen which hardness is known, say for instance fused silica or some other polymeric material for low hardness specimen, and use this equation 1 to obtain the hardness of the specimen. Scratch adhesion test. The scratch adhesion test, which is the topic for the today's seminar, is done by two different ways. One is progressive scratch test, with where a linearly increasing load is applied during scratching, or a constant load scratch test where load is basically constant. Progressive load scratch test is shown on this view graph. You can see that there is a stylus which is used for this scratch test. It started somewhere at some point on the coating, and it is dragged over the surface of the coating with linearly increasing load. And normal force, which is the load, and tangential force, that or friction force or Fx, these two things are measured. After the test is done, optical microscope is used to have the image of the scratch. From the image, we can imagine where this coating is failing. There are failures. Different types of failure modes may be present in a particular scratch test on a particular coating. We also measure other parameters such as acoustic emission or electrical surface resistance or contact resistance of this coating. The normal load corresponds to a particular failure mode is called critical load and denoted as LC. There may be several critical loads for a particular system or particular scratch test, and that's why they are known as LC1, LC2, LC3, and so on. The critical load is function of coating substrate adhesion, stylus tip radius, that is the geometry of the stylus by which you are scratching, loading rate, that is how load is increased with time, mechanical properties of substrate and coating, coating thickness, internal stress in coating, and flaw size distribution at substrate coating interface, and friction between stylus tip and coating. On the other hand, constant load scratch test is done as it implies with a constant load. Load remains constant and you scratch at different load levels. So series of scratch tests are performed with constant normal loads each time, but level may be different, till a point where failure occurs, failure of the coating occurs. Each scratch is examined with an optical microscope for failure. Sometimes the force, that is tangential force, Fx, or other parameters such as acoustic emission or electrical contact resistance also exhibit some kind of changes, sudden changes at the point of failure. They can also be used to pinpoint at what point failure is occurring. The load at which such failure of the coating occurs is termed as the critical load again. Constant load test requires more time because you have to do several scratches, series of scratches, but it provides greater statistical confidence. And progressive load test is suitable for rapid assessment and quality assurance of coating. Hence, it is more popular for research and development work on coating processes. On this presentation, I will concentrate mainly on progressive load scratch test. Coating failure modes during scratch test. There could be two different types of coating failure. One is called cohesive failure, as shown here on the right side. The cohesive failure basically coating fails itself. That is, an example is through thickness coating cracks. It doesn't fail through the interface of coating and substrate. When it fails through the interface, which is called adhesive failure. Examples are buckling, spoliation, chipping. Adhesive failure actually happens due to compressive stress, which is present in the ahead of the cracked, stylus tip, whereas cohesive failure happens with the tensile stress. Tensile stress is the major driving force for cohesive failure. Practical scratch adhesion value of coating is defined as the lowest critical load at which a coating fails. It is an important parameter related to coating substrate adhesion that could be used for comparative evaluation of coatings. Let's examine some of the damage features, how they look like when you do a scratch. There will be several failure modes. There are several of them referred in the literature, especially in STM standard C1624. And those who are more interested, they can refer to those standards. I tried to put together some slides here to show some of the major damage features. I categorized them into two different things. One is like cohesive failure, like through thickness cracking, such as brittle tensile cracking. These type of crackings can have a nested micro cracks open to the direction of scratch. They can be straight, like chevron cracks, or they can be in the form of arc, as arc tensile crack, as shown on the right side of this view. There can be harsh cracking, series of nested micro cracks within the scratch groove. Or there can be conformal cracking, micro cracks that are formed while coating try to conform to the groove. These are open away from the direction of scratch. Direction of scratch is this way, and the conformed cracks opens on the other direction. Other type of damage features are chipping, which are related to adhesion failure. The chippings are rounded regions of coating removal on the surface of this coated specimen, extending laterally from the edges of the scratch groove. Some other damage features related to adhesive failures are buckling, wedging, recovery, and gross pollution. These are mostly happen due to compressive stress on the coating. Coating buckles ahead of the stylus tip, irregularly wide arcs with patches missing on the coating surface, and they open away from the scratch direction. Wedging is similar to that, but here these are more pronounced patched areas where coating actually removed by wedging. They are annular structure and they open away from the scratch direction. Recovery. Regions of detached coating along one or both sides of the groove, they actually oriented along the direction of the scratch, produced by elastic recovery behind the stylus and plastic deformation in the substrate. And gross pollution, where large detached delaminated regions of coatings, where coating has very low adhesion strength, say ceramic coating on substrate. Failure mechanism of coating. If we consider coating and substrate as brittle and ductile materials, they have ductile brittle properties. There are 4 different types of mechanism through which coating fails. You see on this left side coating harness. on the top, substrate hardness. When coating hardness is low and substrate hardness is low, both of them are low, you have most of the time plastic deformation of coating and substrate that produces tensile and conformal crack and mostly buckling failure of the coating occurs. When coating hardness is low and substrate hardness is high, plastic deformation and conformal cracking of coating followed by spoliation and buckling failure in coating as substrate cracks. In the third case, when coating hardness is high and substrate hardness is low, tensile and Adhesion cracks, chipping and spoliation of coating occurs. Substrate actually deforms because substrate has less hardness, so it tries to deform, and chipping and spoliation occurs on the coating. These are the major failure mode. On the extreme case, when the coating hardness is high and substrate hardness is high too, tensile crack followed by chipping and spoliation of coating occurs. Now we'll go through some of these scratch models which are available in the open literature. The Benjamin and Weaver, their model, they propose two models basically based on tangential force measurements at the tip, which is basically Fx, we call it sometimes friction force, and also based on normal force. First model, as shown in equation 2, expresses the tangential force Fx in terms of hardness of the coating and the substrate, that is Hs and Hc. Hs is the hardness of the substrate and Hc is the hardness of the coating. D is the scratch width, T, small t, is thickness of the coating, and R is the radius of the tip, that is the stylus. There are three terms on these equations, equation 2. First term denotes plowing force required to deform the substrate, and second term and third term denotes the force to remove coating from the surface and the plowing force required to put aside the shear film respectively. If we can find out Fx, Hs and Hc are known, thickness of the coating T is known, and if we find scratch width D, we can find the shear stress, critical shear stress at the point of failure. That critical stress could be used for comparing several coating specimens or coated specimens. This particular model worked well for metal coated on glass specimens, especially aluminum, but it doesn't work for some other coating system. Second model Benjamin and Weaver proposed was based on normal force, and it is equation 3 actually expressed the shear stress at the lip of the stylus tip in terms of hardness and contact radius between the tip and the coating A, which is basically half of the scratch width. So this model gives a measure of adhesion in terms of critical shear stress by substituting A measured the critical load. Later on, Olivier and Matthews modified the second model of Benjamin and Weaver, equation 3, by replacing Hs as Fz, that is normal force, divided by A squared. A is the contact radius, half of the coating width, scratch width, sorry. And this, they gave an equation which is shown in as equation 4 here, tau c equals Lc by pi AC root over of R square minus AC squared. So Lc is a critical load and AC is contact radius at the critical load. This model was able to yield semi-qualitative results for DLC film, diamond-like carbon film. Logier considered compressive stress under the leading edge of the indenter and expressed the stress sigma x, that is tangential stress, based on two different parameters. One is with friction, that is mu, considering friction. Compressive stress at the leading edge of the indentation induced by the friction during sliding. Friction has lot of influence on the scratch adhesion of any coating substrate. It has been found that if friction is high, it tends to show less scratch adhesion, property of any coating substrate system. Of course, it is not fully proved, but in most of the cases it has been found and people have worked on this. So Logier tried to correlate this, tried to incorporate friction in this model. Assuming elastic Hertzian contact, the contact radius A is expressed in equation 6 by Logier. And using equation 5 and 6, we can calculate the critical shear stress of the coating. That is adhesion stress basically. When this contact radius is very small compared to the radius of the tip, shear stress can be expressed as equation 7, tau is more or less equal to sigma x into A by R. So if we can find the tangential force at the critical point, we can obtain or calculate the shear stress, which in turn will give you the adhesion strength of the coating. Logier later on also introduced work on adhesion for any particular scratch test, which relates to adhesion strength of any coating substrate system. And they expressed W equals to sigma c square by 2 EC into T, where sigma c is the critical shear stress and EC is the Young's modulus of the coating. T is thickness. This model predicted results on carbide and nitride coatings reasonably. Later on again, Burnett and Rickerby, they considered elastic plastic indentation stress, internal stress, and tangential force, and put forward a model for calculating the critical load LC equals pi d squared divided by 8 to 2 ECW by T to the power half as expressed in equation 9, where W is the work of adhesion, and this is everybody's aim to find out for any coating substrate system. EC is Young's modulus of the coating, and T is thickness, of course, and DC is the scratch width at the critical load. So if we can find, LC can be found out by a scratch test and all other parameters known, so W can be calculated using this model. Boole et al., S.J. Boole, they have worked a lot on this system, coating system, and they define critical load as they replace basically this area term in equation 9, pi d square as AC by mu c into mu c, where mu c is working ratio and mu c is the friction coefficient. They also put for friction, or also it is called as drag coefficient, friction drag coefficient, Stellar's drag coefficient. And A is the area, cross-sectional area of the scratch track at the critical load. A is AC, or AC is actually expressed in equation 11. Using equation 10 and 11, this is the total model, we can calculate the work of adhesion. Although we have several more models probably, which will be very difficult to cover here in this short webinar, but all these existing models invariably use some assumptions and simplification to deal with the inherent complexity of any scratching process, which involves large number of variables. Hence, the existing scratch models experience great difficulties to give a complete analytical description of the mechanics of scratch testing. Hence, predicted scratch adhesion values from such models differ widely from the actual scratch test results. Evaluation and fine-tuning of such scratch models certainly requires continuous developmental effort with an objective to obtain a standard model that would give comprehensive description of any scratching process. While we wait for that, for all engineering purposes, we use some practical approach for scratch testing. In practical approach, what we do is we take a stylus, it can be of diamond or some other material, hard material definitely, and we apply a progressive load from a very small load to a high load, linearly increasing, and we drag over the coating surface and find out by several means, maybe by optical microscopy, where this coating is failing, or by measuring the electrical contact resistance. If the substrate is electrically conducting, if you continuously measure the electrical resistance between the tip, that is a stylus tip, and the substrate, we can easily detect the point of failure when actually tip touches the substrate. The resistance drops to a very small value, and we know where it is failing. In this case, say for instance, R is changing, it dropped at this point, and also the tangential force, which is Fx, basically, it started becoming unstable at the point of failure. It changed abruptly. So this is a practical approach where we find the normal force or critical normal load where coating fails. And this particular parameter can be used as a comparative parameter for comparison of several coatings. If it is pretty high, it implies that coating is good, scratch adhesion of this coating is good. If it is low, means scratch adhesion is low. Bruker has a scratch tester. The model is known as CETR-UMT, and the CETR-UMT can perform several scratch testing, almost all kinds of scratch testing. It can perform constant load scratch test for hardness and adhesion, progressive load scratch test for practical adhesion, and it can measure several things like electrical contact resistance, electrical surface resistance. This is very important when we deal with electrically conducting coating on non-conducting surface. Acoustic emission, in situ scratch depth profiling using capacitance sensor, which measures the depth of the coating when it scratches, coating as well as the scratch depth, and tip displacement. This is another parameter which can be measured in situ to have the profile of the scratch. Optical microscopy and AFM for imaging after the scratch is done, and 3D optical microscopy, which is related to interferometry. This is also used for imaging and metrology of any scratch. This is a picture. There are two pictures here just to show you that it can have an optical system for imaging or AFM. Then it has head and a profiler for imaging and metrology after the scratch test. It deals with one drive which actually moves the specimen for scratching. We can also either move the specimen or the tip by using two different kind of drive systems, slider or linear. And it can accommodate several different probes, say for instance acoustic emission, ECR, ESR probes, which can be simultaneously measured and recorded along with friction force or tangential force and normal force. Normal force, or that linearly increasing scratch test, normal force is controlled by a feedback loop connected to the sensor. Now I will present some of the scratch test results, advanced scratch test results, which are obtained using CETR scratch test. This is a scratch test results. This was done on DLC coating on steel substrate using a diamond stylus 12.5 micron tip radius. This red line shows the normal force which is progressively increasing, and Fx, which is actually showing a sudden change at the point of failure. And on the optical image, you can see that coating has completely failed here. It scratched through the coating. During the scratch, we measured in situ the G encoder, and you see the G encoder plot shows there is a coating depth of about 3.5 micron at the point of failure. This changes. Sample is mounted on the stage. Tip is here. The tips comes here automatically on the script. You just specify what to do, scratching or image scratching. It scratches, and the optical head actually moves automatically to the place where this scratch exists, and it takes series of pictures, and it collates all these pictures together, and it plots with the Fx and Fg data automatically. Here is one profile using an interferometer. We call it K0 of a scratch. So this is the scratch, and similar to the earlier one which I presented in the previous, just the previous view graph, and it shows the coating thickness about 3.5 micron. Another linear scratch, or linear scratch, I mean progressively increasing load scratch or progressive load scratch. This was done on 1 micron thick DLC coating on titanium substrate. Here is the setup shown here on the left top. And Rockwell tip was used, which is 200 micron tip radius. You can see that coating failed at around 25 Newton load. This is a COF, which is basically ratio of tangential force, that is Fx, to the normal force Fg. And if COF directly shows that coating failure, which is corroborated with, again, optical image. Another example where we added acoustic emission probe. And you see this is again 3.5 micron thick DLC coating on steel substrate. Rockwell indenter is used for this scratch test, and with a progressive load, that is linearly increasing load, and it actually started from the very beginning. There are several failure modes on this particular coating with this indenter, Rockwell indenter. You can see some of the chipping started, and some of the, but the interesting thing is that at this point it actually first delaminates the coating, that is, coating is completely failed here. And you see there is no much indication of change in lateral force, that is Fx, but you can see there is an indication from acoustic emission. It started showing up some of the events at the point, from the point of failure onwards, which indicate that actual failure occurs here. At the point of failure, we did some kind of profile of the scratch, and you see the profile here, which shows about 3.5 micron depth of the coating. Here is another example of progressive scratch test with depth profile. This was done on relatively thick coating, 40 micron thick polymer coating on steel, soft coating on steel. And this test was performed with a microblade, tungsten carbide microblade with tip radius 400 micron. It's very sharp. Microblade was used with an objective to measure ECR signal, because tungsten carbide is conducting, diamond is not. And here we use a microblade to scratch this coating with linearly increasing load, and he found that at certain point when coating is scratched completely, you see that ECR signal drops to almost near zero. and from this we find out the scratch adhesion force corresponding FG force, which is scratch adhesion force. During such scratch test, we can also perform scratch depth profile, which is shown at the bottom figure here. Now, here is what we do in this case is like, we do a pre-scan to know the surface of the coated specimen. There may be a tail, so we want to evaluate those, and then we scratch it, progressive load scratching, and then we do a post-scan to measure how much elastic deformation was there, what is the permanent actually deformation after the scratching. And you see on the bottom it shows those two numbers. This is basically when it was scratching. The depth was more because it includes elastic and plastic deformation. But after scratching, that is post-scan, so only plastic deformation. In our software, we have a system of image tagging. You just click on the image anywhere, and you will see the width of the scratch and depth of the scratch. D is the depth, and delta y is the width of the scratch. All these things can be evaluated in a few mouse clicks. Another linear scratch. This is on very soft coating, like zinc coating on steel. And you see in this case, again, since both these substrate and coating are conducting, it's very difficult to evaluate the ECR signal here. Now, it's easier to perform AE measurements on this. You can see acoustic emission measurement shows when this stylus cuts through the coating and started scratching the steel substrate. Lots of acoustic emission events exhibited by this process, and we can pinpoint where it is failing. There is not much indication on the lateral force measurements. There is some kind of instability which started somewhere here at very small load, probably about 5 Newton, but actually the complete failure of the coating occurs at about 10 Newton, somewhere here, which is confirmed by acoustic emission measurements. So these are acoustic emission measurements, resistance measurements, and lateral force measurements are different parameters which will definitively indicate the point of failure of the coating, from where we can actually calculate the scratch adhesion of a coating that can be compared with different coatings. And on that particular specimen, we also did pre-scan, scratch, and post-scan measurements. And our software allows us to do adjustment, like you can do a tilt corrections based on the pre-scan measurements, and those corrections will apply to both scratch and post-scan to have correct values of depth or scratch profile during scratching as well as after scratching. This in turn automatically during the scratch test with the procedure of pre-scan, scratch, and post-scan. Here is another example of pre-scan, scratch, and post-scan using a tungsten carbide blade. CETR-UMT can also be used for doing a different kind of scratch test. Here we use a linear scratch but with a constant load, and using a flat side of a tungsten carbide microblade. You see here on this there is a bump or a polymer dots. Size is about 1 millimeter diameter and height is about 25 micron. You install the blade somewhere here, apply a load, say 4 Newton in this case, and move the blade over this without changing G position. At certain point, it will just scrape through these polymer dots, and you see the friction force or lateral force at the point of starting the scratch. It increases linearly and goes down as it removes the dot completely, scratch to the dots. Area under this fx with distance curve, here it is time plot, but this can be converted into distance because you know the velocity of the movement, velocity of stylus movement. And from this area, when it is plotted with fx versus d, we can have the adhesion energy of a particular polymer source. This could be a comparative numbers, which could be parameters which can be used for comparing several coatings. This gives not force but directly adhesion energy. Energy it requires, or work of adhesion requires, to completely scratch through this type of dots. Now we'll go for 3D scratches. CETR-UMT is a versatile instrument which can perform different kinds of tests. And in scratch test, not only we can do constant load scratch test or progressive load scratch test, but we can also do a 3D scratch where actually we are increasing the load. We are testing with an increasing load along x directions, the normal load using the stylus. But at the same time, the same specimen can move back and forth using the linear drive, and which makes series of scratches, very fine scratches, and this distance between two series of scratches can be well controlled using a script. By this process, you see at certain point, the coating started to fail. It delaminates, it scratches through the coating. You can see on the optical microscope, optical image on the top of it. And this type of test, 3D scratch, actually very helpful to find when coating is really thin and substrate is soft as well. And this was done on a DLC coating on steel substrate using a 12.5 micron tip radius diamond stylus. From this graph, we have an FG plot, and we can find out the force that is a critical load for this failure of this coating. We can also perform XY scratch with reduced spacing or different kinds of scratching. In this view graph, it shows that you can scratch with a constant load, but in two different motions continuously without lifting the stylus. And you can reduce the spacing, subsequent spacing of the scratch till it leads to failure. In this case, the last spacing was about 10 micron, these two subsequent scratches along y direction. And it did not fail. Coating did not show any delamination. But when this spacing is reduced to 5 micron, coating failed. This implies that pre-stressing by making series of scratches actually has a lot of influence on the failure of the coating by delamination. So for instance, in this case, it fails when this distance of separation with two successive scratch was reduced to 5 microns. We can also perform angular scratches with an angle, at any angle. We can program it. We can write a script to perform this kind of scratch. And again, at the end, when it didn't move the slider, it actually failed, coating failed. At the conclusions, CETR scratch tester can perform advanced scratch test, constant load, progressive, 3D, XY, angular, all other kinds of whatever you can imagine, to evaluate the adhesion properties of coating. CETR-UMT test system can perform comprehensive evaluation of coatings by automated imaging and profiling of scratch. I have listed the references here from where I prepared this particular presentation. Thank you.
Okay, thank you, Suresh. Thank you so much. This has been a wonderful webinar. Let me organize a couple of questions. We do have a number of questions from the audience.
Sure.
Let's start with the first one that came in. For progressive load scratch test, there are a number of repetitions I have to do to guarantee reproducibility, or is just one measurement enough?
Good question. You know, in scratch test, one measurement is not enough. You need to repeat it many times. But if you do progressive load scratch test, probably 3 measurements will be fine to have some kind of reliable number, not statistical, I should say. But if you do constant load scratch test, for getting one critical load, you probably have to perform maybe 10 or 15 or maybe 20 scratches. Then you have to repeat it. So you probably will end up doing 50 scratches, for which will be equivalent to 3 scratches under progressive load.
Okay. Following on from that, is there a way to decide between constant or progressive load? And is there a recommended film to use for the constant load scratch test?
Okay, it depends on the user what they want to do, whether constant load scratch test or progressive load scratch test. But progressive load is widely used and popular because it is relatively faster. Now, in certain cases, say for instance, you have a electrically conducting coating, say metal coating on polymer. Now, in this case, if you want to perform electrical contact resistance measurements during the scratch test, it is better to use constant load scratch test instead of progressive load. In this case, probably under progressive load scratch test, you may not be able to find the exact critical load because there may not be much changes of tangential force. There might be, or there may be some kind of changes in acoustic emission events. So either you can measure acoustic emission, but if you want to measure really electrical contact resistance on this coating system where a conducting coating is on the top and non-conducting coating at the bottom, I recommend to use constant load scratch test with electrical surface resistance measurement.
Okay. And that perhaps relates to another question we have here, that some coatings are electrically non-conducting, so can resistance measurement be performed on such specimens, correct? Along a similar vein?
Yes, good questions. You know, most of the time coatings are non-conducting. Say for instance, DLC, the diamond-like carbon coating, most of the DLCs are non-conducting, and it depends, of course, there are different kinds. But in these situations, you can still measure electrical contact resistance, provided you need to have a you use a electrically conducting tip, such as tungsten carbide blade or steel tip, probably, which is conducting, hardened and tempered steel tip. Okay. Now, this is done, and this is very important because when you scratch, since there is a non-conducting coating on the surface of the substrate, conducting substrate, I'm sorry, initially the resistance between the tip and the substrate will be very high because the coating is non-conducting. But when it cuts through the coating and tip touches the substrate which is conducting, you get a very low resistance. So you see a transition when coating fails. So this type of scratch test using a conducting tip or non-conducting coating gives you very easily the moment of failure, and from that, you can calculate the scratch adhesion properties of the coating.
Okay. Okay, there are several questions coming in. The next question has to do with epoxy coating systems. So can we use this test to evaluate epoxy coating systems and evaluate the effectiveness of a formulation and extrapolate the life of a system or the life of the epoxy?
Yes, yes, it could be done, but I need this will be almost like, you know, non-conducting coating on a conducting surface if it is applied on steel or some other metals and alloys. And epoxy coating, of course, it can be evaluated using scratch test procedure. As I outlined, you need to use some kind of conducting tip, maybe a tungsten carbide blade, microblade, and attach it with a electrical contact resistance measurement system in our CETR-UMT scratch tester, and perform a scratch test. You can also attach an acoustic emission sensor to see if at all any acoustic emission coming from the failure of the coating. But most likely this is a polymer, and I have found that in polymer it is very difficult to get good acoustic emission signal. And probably you may not get it, but it's good to try it. But ECR definitely will show. And if acoustic emission signal is really good, probably you do not need ECR, and you can do conventional scratch testing using a diamond stylus, Rockwell diamond stylus, 200 micron tip radius. I presume that your coating thickness for this epoxy system will be really thick, maybe 40, 30, 40, 50 micron, maybe 100 micron. You can really perform the scratch test using a diamond stylus with 200 micron tip radius.
Okay. We have one more question related to this, and then there are several questions about tips and maintenance of tips. So the last question I have here regarding the scratch test itself, we can use scratch testing, I guess this is a question, can we use scratch testing on coatings with super low friction coefficients?
You said super low friction coefficient. Is that correct? I'm sorry.
Yes, super low friction coefficient.
Okay. I believe it can be done. I explained at some point on my presentation that friction has a lot of influence on the scratch adhesion value that we get after performing scratch test on coating substrate system. It has been found that higher the friction, the scratch adhesion value shows lower. So if you have less friction, probably scratch adhesion value will show a little bit higher, which is good. You can easily detect that. So it is possible to measure super low friction coefficient coating using a scratch test procedure. It could be, if it is, again, if thickness is very small, say less than 10 micron, maybe less than 5 micron thickness of the coating, we probably can use diamond stylus with smaller tip radius. Say for instance, maybe 5.5 micron tip radius, or 12.5 micron, or maybe 2.5 micron tip radius diamond stylus, and using a low, using an appropriate force sensor, this test can be done.
Okay, let's move on to some questions about tips in the few minutes that we have left here. What effect will a diamond tip, which is slightly damaged, have? And how often should one check their diamond tip?
Yeah, this is very important questions, because this tip has a lot of things to play with these scratch test results. You know, it has a lot of influence. Tip has to be in perfect conditions. Usually diamond tips are less actually contaminated, or when you scratch it, probably in initial stages those contamination goes, or you can just make some indent to remove the contamination. Now other thing is diamond tip may be damaged during repeated scratch testing. So it is really good idea to evaluate diamond tip before performing any scratch test. You can examine it under a microscope, optical microscope with maybe 40x magnification, and you just look for any damage, any chipping damage. Usually there is a chipping damage on the tip. There could be some kind of this change in radius because of wear and tear of the coating, the wear of tear of the diamond tip for scratch testing for several times, several maybe months or weeks. Now, it is a good idea to examine the tip before doing any scratch test. But I should say that you really do not need to examine in details. Maybe just microscope, optical microscope is enough for this test. But if you think that there is some kind of different where scar is forming, scratch scar is forming, or tip is really bad under microscope, when you look under microscope, then we need to do a profiling using an interferometer or some other profiling device to examine the tip and find the tip whether it has really have 200 micron tip radius or whatever tip radius is supposed to have. So for instance, 12.5 micron tip radius diamond stylus should have that some kind of specified range from the vendor. We need to look into that and make sure that tip is okay to use.
Okay. I think this may be our last time for just this last question. There are a number of others, so I'll just again repeat that we will respond to your questions offline via email and answer, make sure that we get to each one of you. So the last question we have today is how do you select a tip, and what would borosilicate spheres be adequate tips for testing thin DLC films on glass?
I'm sorry, Sarah. Could you please repeat the last question?
Sure. My apologies. How do you select a tip, and would borosilicate spheres be an adequate tip for testing thin DLC films on glass?
Okay. Yeah, I got it now. Thank you. Tip selection is basically done on depending upon what type of application is in mind, but usually it should be sharp so that you really break through the coating, and that's why diamond stylus is very popular. They are sharp. That way they're sharp, not like. But I will prefer not to use any ball for scratch testing. But in some cases, suppose you have to use a ball, maybe say in this case borosilicate glass ball, you can use borosilicate glass ball, but it will be, you need to apply a lot of load. Unless this ball is really small, you have to apply high load and to break through the coating, and it should be okay. But I will prefer using some other stylus, maybe diamond stylus, maybe some say diamond stylus with smaller diameter, maybe 12.5 micron tip radius, to evaluate such coating, DLC coating on glass.
Okay, we are just about coming up on 9 o'clock Pacific time. I want to thank everybody for joining. That is the last question we're able to take, but we will again follow up all these other questions that have been submitted. Great questions will be answered offline. Suraj, thank you.
Thank you, Sarah. Thank you, everybody.
We wish you a great day. Take care, everyone.